Yeah, then good morning, dear school community and dear guests. I feel very honored to welcome all of you in the auditorium. We have all our classes from grade 5 to 12 here, and of course also their dear teachers. We welcome some of our parents. We welcome members of our school board. We also welcome our guests from other schools, St. John, Mentari International School. We welcome, of course, Frau Lorenz. She is head of climate and environment. And of course, we are so proud to welcome our guest of honor, Herr Professor Stefan Rahmstorf. Please give him a big applause. Yeah, now I pass to Frau Lorenz. She also would like to speak some words from embassy.
Yes, dear Herr Hoffmann, dear colleagues from the DSJ, dear students, I'm very glad that we've been able to be your guests today, and especially that renowned Professor Rahmstorf from Potsdam Institute for Climate Impact Research has taken on the far journey to come to Jakarta and enlighten us about questions of climate change, what are its causes, how it's impacting us, and possibly what can be done about it. Because it's certainly a decisive power shaping all of our future. The younger we are, the more. And therefore, I'm excited to learn from his lecture. Thank you.
Ja, vielen Dank, Frau Lorenz. So, dann kommen wir jetzt zu unserem Ehrengast, Herr Professor Stefan Rahmstorf. You are one of the best-known climate researchers in Germany, if not worldwide. You are professor of ocean physics at the University of Potsdam, head of the Earth System Analysis Department at the Potsdam Institute for Climate Impact Research, and you wrote 4 books about climate and weather. Before we get to the extremely important topic that you will present us today, as we have so many young people here who are all on their way to graduating from high school, can you explain them briefly about your decision what to study and your path?
Dear students, guten Morgen, everybody. I am maybe a bit special in that I already knew when I was 12 years old that I wanted to be a scientist, and after that I never, maybe because as a child I got these experimental kits, and so I started to do experiments as a child, and then I became very interested in astronomy, and as a high school student I spent lots of time at our local university library in Konstanz in South Germany and studied astronomy books. And then I started to study physics after the end of school. And after 2 years of physics, I decided I go abroad for a year, and I was looking at what should I do. And then I saw, and I had actually read a book by Elisabeth Mann-Borghese, the daughter of Thomas Mann, the famous German author. And she had written a book about the world ocean, and I was really fascinated. And then when I wanted to go a year abroad, I looked at what is available, and I saw one can study ocean physics, physical oceanography, and I thought, wow, that is what I want to do, because as a child I always loved being by the ocean and building sand castles and things like that. And yeah, after I did 1 year of oceanography in Wales, in Great Britain, I had decided that's what I want to do. And yeah, now I'm professor of physics of the oceans, and it's my dream job.
Okay. Yeah, thank you very much. I know our students and everyone here in the auditorium will have the chance later to ask you additional questions. I would propose to start with your contribution now for us, and Frau Lorenz and I will leave you here. The auditorium is
I'm
yours. Yeah.
Can you click? Oh, I can click myself. Sorry, because that's if it works. Oh, it goes the other direction. I see. Okay, that's my starting slide. So there you see me as a somewhat younger person on a research ship. I did my doctorate research in Wellington in New Zealand, and I went on some research cruises in the South Pacific. Can we get less light in the front so the slides are better visible, perhaps? On the right-hand side, you see what happens on the ship when there is strong waves going on. I took that right-hand photo out of the window of my little cabin on the research ship, and I realized, gosh, down there where this big wave is washing over the deck, I had just been walking along 5 minutes before, and if that wave had come then, I would not be here today. I would have been washed overboard and dead. And I was a bit shocked that this was my first research cruise as a PhD student, that nobody had warned me that I must not walk on the lower deck in such weather conditions. Anyway, so I did survive, and I'm here today to talk to you, and I'm very glad about this. So I want to talk about climate change and the oceans, and I'm starting with climate change, and then I will talk about the oceans. And I'm a great fan of Alexander von Humboldt, the great German explorer, scientist in the 19th century. And I actually went on a high school called Alexander von Humboldt Gymnasium, and there are many such high schools in Germany. Even my kids now go to Humboldt Gymnasium, but in a different city, in Potsdam. And but that's not the reason why I show Humboldt. I show him here because he was one of the first, maybe even the first person in the world who wrote that humans are changing the climate. A quote by, I don't know this quote by heart, so I have to read here. By cutting down forests and by releasing large amounts of steam and gas at the centers of industry. So he was ahead of his time, and in that respect, like in many other scientific issues, it is also known that Humboldt knew about the greenhouse effect, because the greenhouse effect had been discovered in 1824 by a French scientist, Joseph Fourier. Now, of course, what Humboldt didn't know is the detailed understanding of how our planet Earth works, the energy balance of our planet, because, you know, the temperature, of course, is determined by the flow of energy, how much energy comes in. You see that on the left-hand side, the yellow arrows are the energy from the sun coming to the Earth, surface temperature. One at the right here is the biggest one. It's the greenhouse effect. And that is exactly what we are changing by burning fossil fuels and adding more greenhouse gases to the atmosphere. The result is this. This is the famous warming stripes. Every stripe shows the temperature of 1 year for the whole planet, the globe, the Earth's surface temperature. Starts on the left in the year 1880 and ends with last year here. And now I added just a curve showing exactly the same data. It's a different way of showing these data. And you just see that towards the right, towards the recent years, it's getting hotter and hotter on our planet. And we've already seen a temperature increase by 1.2 degrees Celsius. Now, this warming was predicted before it was observed. Actually, already in the 19th century, I told you about Humboldt, and there were even estimates of how strong that warming from CO2 emissions would be already in the 19th century. And in 1965, there was the first official government report on the coming global warming due to fossil fuel burning. It's a famous Revell report ordered by the American president Lyndon B. Johnson. And it concluded that by burning fossil fuels, we would see a global warming, melting ice caps, sea level rising, and so on. All the things that are happening now were predicted already back then. And in 1988, the famous NASA climate scientist Jim Hansen was the first one to state in a Senate hearing in the United States that the long predicted global warming is now visible in the measurements, in the observations. It made the cover front page of the New York Times, for example, and worldwide as well. And that was, I remember this day very clearly when this was on the cover worldwide on the newspapers, because that was at the time when I was doing my doctorate studies in New Zealand, and it was much discussed. There were some conservative professors that said, oh, maybe Jim Hansen was leaning out the window a bit too early. It could still be natural variability. We're not sure. By now, of course, nobody believes that anymore in science, because it's very clear global warming has been proceeding for decades exactly as predicted, and even quantitatively, not only predicted by academic scientists from universities, but also by scientists from the fossil fuel industry. They kept that in internal document and told the public a completely different story, but they knew also exactly what they were doing with selling the fossil fuels. There was also a big international panel set up to study the problem, the IPCC. And the IPCC is a collaboration where hundreds of scientists every few years put out a report about the state of global warming. And the first one was in 1990. And that already concluded that it is certain that the greenhouse gases will cause a global warming. That was just simply well-established science even back then in 1990. And then in 1992, there was a worldwide summit by leading politicians on how to tackle this problem. And that was in Rio de Janeiro in Brazil. That's why it's called the Rio Earth Summit. And at that summit, all nations jointly decided to prevent a dangerous climate change. This is the United Nations Framework Convention on Climate Change that was passed there in 1992. And I also very much remember this day when the news came out in the evening on the television that this Rio Earth Summit had passed this treaty to prevent dangerous climate change. And at the time I thought, oh wow, finally politics takes this problem seriously and has passed a worldwide treaty to combat global heating. Now, as you see on the temperature curve, so far this has not been very, very successful, because most of those countries that promised to prevent a dangerous climate change haven't actually done very much to keep that promise. In 2015, finally, a much more effective treaty was passed to stop global warming, the Paris Agreement. Again, every single country has agreed to that, and I'll come back to that at the very end of my talk. The temperature here is shown again in the bottom blue curve, those 1.2 degrees warming that I already mentioned. Here shown the temperature for the last 2,000 years, showing quite clearly how we have exceeded the global temperature that by a large margin that has happened in the last 2,000 years. And on the top curve you see the increase in the amount of carbon dioxide in the atmosphere. And this carbon dioxide is a gas, a molecule with one carbon and two oxygen atoms. That's why it's called carbon dioxide, one carbon, two oxygen. And this is a molecule that intercepts that long wave radiation on the way out to space, and that's why it traps heat and leads to increased warming. That, as I said, that's known since the 19th century, that carbon dioxide has those properties, and we are drastically increasing the amount of carbon dioxide. This diagram just shows that there's more carbon dioxide in the air now because of our fossil fuel burning and deforestation than has been in the last 2,000 years. But we have data going back much further, showing that we have seen never such high carbon dioxide amounts in the atmosphere in at least the last 3 million years, most likely even in the last 15 million years on this planet. And here you see the global temperature since the last ice age. I hope you learn in geography lessons what causes the ice ages on Earth. I did learn that in geography lessons in the 1970s, because that is actually something that was scientifically cleared, demonstrated in the 1920s, so more than 100 years ago, by a scientist called Milutin Milankovic, that the cycles of the Earth orbit around the Sun cause the ice ages. This is just a problem of astronomy, basically, and Milankovic, he was in prison at the time when he worked out all the Milankovic cycles with pencil and papers, because he had a lot of time on his hands. He was not in prison because he was a criminal, but because he was politically prosecuted, and he spent years in prison and spent his time working out these orbital cycles. Nowadays, with computers, we can compute those, of course, very quickly, but he had to do it all with just his brain and pencil and paper. And so these orbital cycles are now called Milankovic cycles, and you can look that up at Wikipedia if you like. So that's the reason of the ice ages. And the last ice age was about 20,000 years ago. And here you can see the transition to the Holocene warm period that has been going on for the last 10,000 years. And at the beginning of the Holocene, our ancestors, Homo sapiens, discovered agriculture and started to settle down. Before that, they were hunters and gatherers. In the Ice Age, the humans lived as hunters and gatherers. But since the beginning of that stable Holocene climate, we have done agriculture, built cities, and so on. So all of the human civilization has developed in this stable climate of the last 10,000 years. Now we have left the Holocene behind, and the geologists, they are now calling the epoch in which we live the Anthropocene. That is the human age. That is because humans have now become a geological force, really changing the climate of the entire planet. And you can see the rapid temperature rise there outside the range of natural variations of the Holocene. And also, if you look at the speed of this warming, at the end of the Ice Age, due to these Earth orbital cycles, when the Ice Age warmed up into the Holocene, the global temperature rose at a speed of about 1 degree per 1,000 years. Now we have warmed already 1 degree in 100 years, so it's going 10 times as fast as these natural cycles that have occurred in the last 3 million years. And if you may have seen it in the media, what happened last month in September. This is the global temperature of September, and you know, the last year has beaten the previous record warm September that was in 2020 by 0.5 degree Celsius. This has never happened before. This is 5 times larger than any new record that occurred in the entire history of measurements. And one of my British colleagues has called this temperature record gobsmackingly bananas, because it's such a crazy measurement. And we still don't fully understand why we get this sudden jump in temperature. Because scientists are usually very sober, the fact that he used this expression made it a little bit famous, and many newspapers reported it, and the Guardian actually had a cartoon about that, joking that scientists had come up with a new temperature scale that goes from gobsmackingly bananas to butter-clenchingly not so, to pen-scrappingly bonkers, because, yeah, that's, I think it's a kind of nice joke, even though it's not really funny what is happening now to our Earth. So, I often ask audiences what they think, how much of the modern global warming is caused by humans, and surprisingly, even after so many decades of science and media coverage, etc., most people don't know that it's 100%. People guess maybe 60%, maybe 80%, but it is 100%. That's from the last report by that IPCC, but the previous report published 2014 had a similar diagram showing exactly the same. We can calculate how much human-caused warming there is because we understand this energy balance, and it is monitored all the time by satellite, by radiation measurement network on the ground, so we know how much human-caused warming there is, and it is exactly the same as the observed warming. And we also know that there are no natural reasons for any warming in the last 100 years. These Earth orbital cycles are far too slow and not really pointing towards warming right now. The solar activity has declined in the last 70 years and has slightly counteracted the warming that we have been causing. So probably we have even caused slightly more than 100% of the warming, because natural cycles have tended to counteract that, but only to a very small degree, because they're much weaker than what we have been doing. We're kind of slowly coming to the ocean now, because this is a picture of the northern hemisphere ice cover. You can see the sea ice on the Arctic Ocean. Sea ice is simply frozen ocean surface, just like when ice forms on a lake. I guess you don't get this in Indonesia, but where I live, lakes freeze over in winter, and the same happens to the sea. And on the Arctic Ocean, the layer of sea ice is about 2 meters thick. So from the floor to about here, that's how thick the sea ice is. In contrast, the continental ice, that is ice that forms by falling snow on the continents and never melting, so the snow piles up and piles up and piles up. That is on Greenland here. You see the Greenland continent, the island and its ice cover. That is 3,000 meters thick, so it's so thick that it's like a high mountain range. This is a very different thing, but the sea ice, because it's so thin, is very vulnerable to melting with warming, and so we now have a situation like this. Let me go back. It was like this up to the 1980s. Now it looks like this, and everyone who is sitting in this room, I think, will live to see this situation where for the first time we will have a virtually ice-free Arctic Ocean. And of course that really takes the ground away under the feet of the polar bears, but that is not the only problem. It will totally change the Arctic ecosystem, all the marine life there, and it also has a strong influence on our weather in the northern hemisphere. And we also know, at least here 1,400 years back, how the sea ice cover was on the Arctic Ocean. You can find that out by drilling into the sediments at the ocean bottom. They tell you whether there was ice above or not. And yeah, we see this drastic decline in the 20th century. It's really going downhill with the ice cover. And my colleague in Potsdam, Markus Rex, in recent years he had been leading a big North Polar expedition with the German icebreaker, research icebreaker Polarstern. They let the icebreaker freeze into the ice and drift over the North Pole in this expedition. That was the first time that had been done. And Markus came back and, where's the quote here? He said, we watch the sea ice dying. It's not only the sea ice, but also that continental ice that is melting that I told you before. Of course, that takes much longer because it's 3,000 meters thick, so it's not going to vanish anytime soon, but it's melting back as the satellite data show. This is NASA data for the ice on Greenland and the ice on Antarctica. And, well, you can see clearly the decline, and you can always look at these measurements of how global warming is proceeding, how the ice is melting, etc. on the NASA website. They have this very nice website called NASA Vital Signs. It's written here as a source where it's continually updated, all the data, and you can, if you want to get solid information on what is happening with our planet in terms of the climate, that is one good place to look. Okay, I'm coming to the ocean part now. This is a view of the Earth if you look down onto the middle of the Pacific. And you can see from that side, when you look at the Earth, it shouldn't be called Earth. It should really be called ocean, our planet, because from that side it's almost entirely ocean. Overall, more than 70% of the Earth's surface is ocean. So land is really a minority. Most of our planet is covered by oceans. And that's why, obviously, they are very important. Now, the oceans are also warming. This is the trend in the ocean surface temperature for starting since the 1950s, how much they have changed. And you can see practically the entire ocean surface of the world has warmed up in the last decades, just like the land surface, only not as much because the ocean take longer to warm up. You know, as if you try to heat up a pot of water on the stove, you know it takes some time because water has a big thermal inertia. That means it can store a lot of heat, and so it requires more heat to heat up water than to heat up air. And that's why the oceans are warming more slowly than the air over land. But they are also warming everywhere, with one big exception in the northern Atlantic. That is one of my main research areas already since the 1990s, is what's happening to the North Atlantic, and I will come to that in a short while. We can also measure the heat content of the ocean for the top 2,000 meters. So that is now not the temperature, but it's the amount of energy, of heat energy in the oceans, and that is increasing very steadily, and it's a staggering amount of heat actually, because water has this really big storage capacity for heat. And that actually, from the extra heat from our Earth energy balance that is trapped by the increase in greenhouse gases, more than 90%, about 93% go into warming the ocean because of that large heat storage ability of the ocean waters. And that heat content, for example, is very important for tropical storms. The hurricanes draw their energy from the upper ocean, and so the warmer the upper ocean gets, the stronger the hurricanes of the world are getting, like the one that just recently, 2 weeks ago or so, devastated the city of Acapulco in Mexico. But there is not only physical consequences of that ocean warming, but also the life in the oceans is quite affected by the warming. One of the effects is so-called marine heat waves. We humans, we suffer from heat waves at the surface, but marine life also suffers from heat waves in the ocean, and they are getting more and more frequent and widespread. Another effect is coral bleaching that is linked to marine heat waves, because corals have a limit of how much warming they can stand. Then there is a loss of oxygen. Warmer water can contain less oxygen, and also the oxygen in the ocean is depleted by decaying biomass, but it is replenished at the surface from oxygen entering the ocean, and but it now is trapped more near the surface because the mixing of the ocean gets less and less if you warm the surface, because warmer water is less heavy, less dense, and tends to float at the surface. And so the oxygen supply for the deeper parts of the ocean is reduced by warming the ocean surface. And then we have another problem. The ocean is getting more acidic. That is not a consequence of the warming, but a direct consequence of the carbon dioxide, because about a quarter of the CO2 that we pump into the atmosphere by the fossil fuel use and the deforestation actually enters the ocean. So the amount of carbon dioxide is not only increasing in the atmosphere, it's also increasing in the upper ocean. And when you dissolve CO2 in ocean water or in water, you get carbonic acid. It's exactly like in the mineral water bottles that you can buy that have CO2 in them. It's carbonic acid, or in Deutsch Kohlensäure. The name already says that's an acid, and it makes the ocean waters more acidic. And that is a big problem because the acid starts to dissolve the shells of seashells and damaging plankton growth and so on, and also affecting the corals. So just a little bit about the coral reef issue. Corals usually are living together with tiny plankton organisms. They're called zooxanthellae, and they make the corals so colorful. Like if you look at that left picture, that coral branch on the far left here, it looks orange. That is because it's alive with these microorganisms there. I'll answer questions after my talk, okay? Remember your question. And so the problem is when a certain temperature limit is exceeded, it's getting too warm, not for the coral itself, but for this the plankton that lives on it, and it abandons the coral, and that's when the corals turn white. And that is called coral bleaching. And that is a sign the coral is in big trouble. It can recover from that, but it takes many years. And if it gets too hot again within the next 10 years or so, then the coral will actually die. And it will be overgrown with algae, basically. That's then a dead coral. And this is happening worldwide now. Here's some pictures on the right-hand side showing the Great Barrier Reef in Australia, the largest coral reef, and it shows which part have bleached in different years, in recent years, and it's always been exactly where the marine heat wave has been. That matches exactly where the coral bleaching is. A kind of ridiculous and sad thing is that if you look on social media, tourists are posting photos of coral reefs that are bleached, that are totally white, and they're saying, oh, look how beautiful the coral reef looks, and they don't know that they're looking at a dead reef there and that it's really a tragic picture. And so my friends and colleagues from Australia who are coral reef scientists, they often make snide remarks about these ignorant tourists not knowing what they're actually looking at here. And so here again you see a coral in Australia. The left half is when it's bleached, and the right half is afterwards when it's overgrown with algae and then it's dead. And a survey of 100 coral reefs worldwide in 2015, 2016 has shown that most of them have been affected by bleaching, also in this region here around Indonesia. So this is a problem that has been predicted by scientists for many years, and it's one of the tipping points of climate change, that corals have this limit how much heat they can stand, and they are basically dying now. That's a very, very sad fact. The sea surface temperature are also strongly affected by the El Nino phenomenon that I'm sure you all have heard about, because Indonesia is very strongly affected by El Nino. El Nino a priori is a natural climate variation. This is the current situation. You can look it up anytime at this website called climatereanalyzer.org, and I downloaded this here on November the 3rd, last Friday. You can always look at exactly what is the sea surface temperature doing, and all other aspects of weather like air temperatures, jet stream, etc., etc. It's a great website. Now, El Nino is this warm tongue of water along the tropical Pacific that is kind of like emanating off the coast of South America. And it has to do with the Humboldt current. This is a big current going up the coast of South America, named after Alexander von Humboldt, who also was the first person to describe this current. And this current brings cold water up the coast, then going across the tropical Pacific. And when this current gets very weak, then there is this anomalous warming along the equator. So the El Nino phenomenon is directly linked to Alexander von Humboldt's name in this way, because it's driven by changes in the Humboldt current. And so that is the El Nino situation. The opposite of that is called La Nina, and that has a anomalous cold tropical Pacific Ocean. By the way, it's called El Nino because fishermen in Peru called it that, because El Nino means the child in Spanish, and they named it after the child because it refers to the Christ child, because the El Nino warming anomaly tended to happen before Christmas. And so that's why they called it El Nino. And of course, this year, the El Nino was already really developing strongly in September. So that's also quite anomalous that El Nino has started so early this year. But overall, it's just a natural variation. And the IPCC has concluded that we can't tell yet to what extent climate change has affected it, because the effects of climate change are still smaller than the natural variations, and that's why you cannot tease it apart. It doesn't mean that climate change has not affected it, but it means we're not sure. We can't really work out how much the effect of climate change has been, but the models suggest that in the future the variations will become more extreme, so with stronger El Nino events and stronger La Nina events. So both ends, the warm and the cold events, tend to get more extreme. And it has a big impact on Indonesia as well, because on the western side of the Pacific, where we are here, you tend to get drought in Indonesia and Australia when there is an El Nino event, because the air rises above the warm water, and the warm water is now on the eastern side of the Pacific near South America, and that's where the air rises. And when the air rises up, that's where the rainfall is. I won't explain the physics why that's the case, because for lack of time, but it's also very elementary physics. Now, another result of global heating on the oceans is sea level rise. There are two main reasons for that. The first reason is that water just expands when you warm it up. So that is called thermal expansion. And that's why inevitably, if you warm up the oceans, they will expand, and that's why sea level rises. That's about half of the sea level rise. The other half of sea level rise is coming from ice melting, continental ice, mountain glaciers, the ice sheet in Greenland, the ice sheet on Antarctica. These are melting, as I showed you before, for Greenland and Antarctica, and that is the other half of sea level rise. I took this photo in Venice, and you might just see it here, a couple taking a selfie there on the Piazza San Marco in Venice. I was actually in Venice there not for tourism, but for a sea level rise workshop which was held there, because of course Venice is greatly threatened by sea level rise, and they have now completed a huge barrier that they can close when there is a storm bringing in water, because Venice is slowly sinking. And so that whole piazza where you can normally walk along is flooded more and more often the more the sea level rises. This is what the data show about sea level rise, and you can see it's not only rising, it's risen by about 20 centimeters in the last 100 years, but the rise is already getting faster and faster. That is shown both by the satellite data and also the tide gauge data. The blue is the tide gauge data. Oh, I have a version of this graph. I just see that's not the best one here, where the tide gauge data are also shown up to the present. Here they end where the satellite record begins, but the tide gauge measurements, of course, have continued, and they show exactly the same as the satellites during that period where they overlap. Why does sea level rise get faster and faster? Well, that's quite logical because it's getting warmer and the ice is melting faster and faster the warmer it is. So the big ice sheets, they are melting faster and faster, and that's why the sea level rises faster and faster. The sea level actually doesn't rise the same everywhere because the ocean surface is not flat like your bathtub water, but it actually has little mountains and valleys, and can differ by roughly 1 meter between different places depending on the winds, for example. And so this is the map showing where the sea level has been rising more strongly and less strongly in various places. That can be mapped by satellites because since 1993 we have satellites that measure sea level with millimeter accuracy from space. That's quite a feat of technology that we can do that. Now, if you want to know what happened previously, you can, for example, look at things like this, a photo I took on the Italian coast of Roman fish ponds. They built these ponds so that at high tide, seawater would come into the ponds to replenish fresh water and nutrients, etc., for the fish that were living in there, that they grew there for eating. And so these ponds were built exactly near the sea surface so that the high tide would wash water in, etc. Now, if the sea level had been rising for 20 centimeters per century already for 2,000 years, that would have been 4 meters, and then these Roman fish ponds would be completely covered by the ocean. They would be in 4 meters depth, but they're still at the sea surface, and that just shows that the sea has not been rising at this rate that we have seen in the 20th century in the past. That is just one little piece of evidence that you can see in the IPCC reports as well, but we actually now have much better data. Here I'm shown together with American colleagues doing some field work on the American coast, a drilling course in coastal salt marshes that are areas that are covered with water at high tide, but they are kind of growing plants, and you can drill in there and you can analyze at what rate the sediments have increased and they grow with the sea. And that's how you can reconstruct sea level for thousands of years back. And the resulting curve that we published is this. This has been done now by many scientists around the world, so we have reasonably good global coverage of sea level data for the last millennia. But that was the first study to do that. And you see how exceptional the sea level rise in the 20th century is here. And actually our paper that was published was even taken up by Obama in one of his speeches to the nation, where he mentioned our sea level rise study. Now, for the future, of course, we expect sea level rise to accelerate further the more it warms. So once we stop global warming, we don't stop sea level rise because it takes many hundreds of years for the ice sheets to melt completely. But by stopping global warming, we can prevent that the sea level rise gets even faster. Once we stop global warming, sea level will rise steadily at the rate it has done in the last decades. But if the more we warm, the more it will accelerate. That is, again, very simple physics. And, we are seeing here IPCC saying by the end of this century we're talking about 0.5 meter to 1 meter of sea level rise, so that's a lot more than the 20 centimeters that we have seen in the last century. And there's a big uncertainty to much higher sea level rise because of possible destabilizing ice sheets which start to slide faster into the sea. Then it could go much more rapidly. That's why there are these dashed lines. And you know, for places like this, Male, the main island of the Maldives, obviously this is catastrophic. And the Maldives are already building a new island which is 2 meters higher, where they want to resettle much of their population. I showed you the transition from the Ice Age into the Holocene in the global temperature earlier on. We also have the sea level data from the Ice Age into the Holocene, and sea level rose 120 meters. So this is huge. And we have, and that means that 2/3 of the continental ice sheets that were present in the last Ice Age were lost in the transition to the Holocene in response to about 7 degrees Celsius warming. Now we have 1/3 of that ice left. That's the ice on Antarctica and Greenland, and that's enough to raise global sea level by 65 meters. That's not going to happen, so don't worry about 65 meters of global sea level rise. But what it does show, you know, because Antarctica is on the South Pole, is very cold, only a part of that will melt, maybe 3 meters of sea level worth or so. But what it does mean is we cannot even afford to lose a few percent, a tiny proportion of the land ice that we have now on Earth without causing a catastrophe to many coastal regions. Okay, my last point about impact on the oceans is the impact on ocean currents. And I have studied for 30 years now, or more than 30 years, the Atlantic overturning circulation. It's called the AMOC, that stands for Atlantic Meridional Overturning Circulation. Overturning because it kind of overturns the whole water mass down to several thousand meters in the ocean, with water sinking down to the depth in the northern Atlantic. And meridional just means in north-south direction. So, you know, scientists like to use these strange terms. So that's why it's called the AMOC. And the AMOC, the Atlantic part, is actually part of a global overturning circulation. The schematic is shown here. Of course, if you look at ocean current pictures that look like this, where the currents look like rivers in the sea, that's not how it really works. This is just a simplified schematic. Here is an animation of that. This is one by NASA showing that overturning circulation. So you have a warm flow northward going around in the northern Atlantic. This is where the water then sinks down to depth between 2,000 and 3,000 meters. It takes a little while to evolve here. So I can explain why does it sink down? Because first of all, it's cold and it is relatively salty, and you need these two things to make the water quite heavy, because the density of seawater depends on the temperature and on the salt content. And now we zoom out and we see the warm surface flow going north, and at depth you see a return flow returning to the south. And so it works like a central heating system. Probably you don't have central heating in Indonesia, but a central heating system, basically you have warm water going into your heater, giving off the heat to the room, and then returning cold the water. And this is the same thing happening here. You have warm water going into the North Atlantic, giving off the heat to the atmosphere, getting cold the water, sinking down and returning as a cold current to the south. So it's a central heating system for the northern Atlantic, and actually the whole northern hemisphere is warmer than the southern hemisphere because of this effect. Now, I told you this is just a very simple schematic. The real ocean looks like this. It's very turbulent, you have lots of eddies. We know this already, of course, from shipboard measurements, etc., but you can see it beautifully just by those satellites that measure the sea level, because those satellites, they can also see where the sea surface is sloping. And when the sea surface is sloping, it has to do with currents because of the Coriolis force. Have you learned about the Coriolis force in physics lessons? Maybe not. That is a force that acts on any rotating system like our Earth rotates, and so water in the northern hemisphere that flows north is pushed towards the right by the Coriolis force, and that sets up a slope in the sea level. Of course, the Coriolis force doesn't act on the equator, so in Indonesia it's probably not a thing, the Coriolis force, because it's zero near the equator. But everywhere else on the planet you have this Coriolis force. That's actually the reason why in this diagram you see nothing near the equator, because the Coriolis force just vanishes there. But everywhere else you see slopes in the sea surface, and they are directly linked to currents, so you can see all the ocean currents just by plotting the slope in the sea surface that the satellites measure. And so you see the Gulf Stream in the North Atlantic. It's this red band that is part of that AMOC, part of that overturning circulation. Now, a funny thing is happening when you look at the change in sea surface temperature. I showed you a global picture already earlier on where the North Atlantic was the only part of the world that has cooled in the last 100 years. It has cooled in the last 100 years. That diagram showed it since the 1950s. This is one that shows it since 1993, since we have really good satellite data. It's a famous cold blob in the North Atlantic. So what causes that? We can basically turn to models, and the models predict exactly this. So if you look at the report by the IPCC, what the models predict for the year 2100 in terms of surface temperature change, they predict the entire globe is gonna heat except for the North Atlantic. And the ocean in a climate model looks like this. So that is actually a simulation based on the basic physics equations, the Navier-Stokes equation that determine fluid dynamics and so on. And you can then get an evolution like that. Video is stalling a little bit, but whatever, doesn't matter. You see the warm band of the Gulf Stream in red. It's showing the temperature here. All these little meanders, etc., that you also see from satellite, they all happen in an ocean simulation in a climate model as well. And when you take this climate model and look at the temperature change when you increase the CO2, you get this funny pattern here after subtracting the global mean change. So everything that is blue has warmed less than the global average or cooled. And that is what the model shows. And in the model, we are like gods, basically. That means we have all the information. We know exactly, it's all in our computer, so we can analyze every detail of what is happening, and we can even run experiments to try things out with the climate models. And so we know that in the climate model, this cold blob is due to a slowdown of this Atlantic Ocean circulation, because I told you it brings a huge amount of heat to the North Atlantic, where it releases the heat to the atmosphere. So if you slow that down, it brings less heat to the North Atlantic, and that region cools. And this is exactly what the models predict, and it is exactly what's happening in the data. This is the data now starting in the late 19th century, so the 100-year trend, more than 100-year trend, and it shows the Northern Atlantic is actually, it's cooling, whereas the rest of the globe has been warming.
And disturbing, that is. You recall what you said in New Delhi about how polar melting might disrupt the North Atlantic current?
Yes.
Well, I think it's happening.
This is from the movie The Day After Tomorrow. Who has seen it? Has anyone seen it? Oh yeah, quite a few. Okay, so this, of course, is a disaster movie, Hollywood, you know, it violates all the laws of physics, basically, but it is based on the realistic scenario of this Atlantic overturning circulation. In the movie they call it the North Atlantic Current, breaking down in response to global warming. So it's a fictional story based on a real concern that scientists like me are studying. So now I want to talk about what we can do about it. See what the time is. Yeah, I think I can probably quickly get through this. It's just 5 more minutes. So first of all, I want to tell you, don't get duped by all the stuff that is circulating in social media, etc., disinformation on climate change. It has its origins in massive disinformation campaigns from the fossil fuel industry, so you have to be very careful to check your sources when you read anything on the internet about global warming. Go to the real science sites. I mentioned a couple like NASA's Vital Signs, etc., if you want to know what's really going on. And also the media, unfortunately, are promoting a kind of distorted view by this kind of both-siderism. They tend to kind of, to any article, ask somebody who claims the opposite or so. And so many people don't know that there is a scientific consensus on global heating and the reasons for global heating. They get the impression from the media that this is still debated. That's not the case in the scientific community and hasn't been the case for decades. There is a consensus in science on this topic. And based on that consensus, we have the Paris Agreement, which I mentioned earlier on, where all the nations of the world, even those that live by selling fossil fuels, like Russia or some Arabian countries, even those have agreed to limit warming to well below 2 degrees, and they have committed to pursue efforts to limit the warming to 1.5 degrees. And this is of vital importance really for all of your future. And so I think everyone should try and convince their government to do their bit, including me trying to convince the German government that they have to make their contribution, because as individuals, we can't really solve the problem. Of course, we can save energy, and you know, I have a heat pump and a solar system, solar panels on my roof, etc. But overall, it's the main responsibility of governments to set the rules so that we get the grip on this problem. I'll skip this as just an atmosphere part of the climate model. So the big problem is that because of all that disinformation, propaganda, there has been so much delay for decades since we've had this framework convention on climate change in 1992, and warming has continued and continued because people haven't acted enough. We now have very little time left. If we want to limit warming to 1.5, we have to go down with very steep decline in emissions, like the blue path here. So cutting global CO2 emissions in half by 2030. So we really have to hit the brakes full on. That is really tough, you know. It's an emergency, like many scientists have said. The good news is we can actually do that. We have the technologies now. And the IPCC also describes how to do it. Other institutions like the International Energy Agency have described that as well. And there is a lot happening, so don't become, you know, depressed or too pessimistic. We have the chance to turn this around, and the International Energy Agency has released a report showing that last year, from all the world's investments into energy, into electricity generation, more than 80% have gone into renewables. So it's, you know, investment in fossil fuels hasn't stopped yet entirely, but it's now a minority. Mostly people are investing in renewable energy. It just has to become faster, but the good things are growing exponentially. This is the photovoltaic panels growing exponentially, wind energy, batteries, electric vehicles, it's all growing exponentially, and the prices are dropping dramatically. The price of solar energy has dropped. It used to be really expensive when I was young. prohibitively expensive. Now, in most countries of the world, it is the cheapest form to generate electricity. And the pressure is also mounting worldwide to actually do something. There's a big youth movement. This is my hometown, Potsdam, relatively small university town, and you see a big process there for climate policies. And Fridays for Future movement has been staging protests worldwide and has really shifted the politics already quite a bit. Not yet enough, we need to do more, but things are definitely improving. We may be right in a social tipping point where we finally, the politicians, start to take the climate crisis seriously and treat it like the crisis and emergency that it has become. With that, I'm at the end, and I want to conclude saying, we are in the middle of a climate crisis based on greenhouse gas emissions. It's about 3/4 fossil fuel, 1/4 deforestation and other land use changes. The oceans are affected by this in many ways, as I have shown, and also many millions of people are suffering the consequences. And so politicians have made many promises in these conferences, but they haven't acted enough, and we have to raise the pressure so that they actually do that. And I skip this, and thank you very much for listening to me, and I'm happy to answer questions. Thanks. Thanks.
Okay, thank you very, very much for this really interesting, but on the other hand also, of course, a bit frightening. Now we could ask some questions, and it would be really nice if I could maybe from class 5 get some helpers. Where's class 5? Class 5 and class 6 is also fine. Someone would like to help to pass the microphone to the ones who would like to ask questions.
If the oceans get colder, will the sea rise stop?
Yes, because if the oceans get colder, then also the air temperature, so of course then the thermal expansion of the oceans will stop, but also the air temperatures will also get colder, because actually it's mostly the ocean surface that determines also the air temperatures on the globe, so that would also stop the ice melting on land if the oceans get colder. However, there's no reason why they would get colder.
How do you like your job?
I didn't understand it.
How do you like your job?
How do I like my job? That is a good question, actually. I told you I love doing science, and so I really like my job in that sense. But sometimes I get depressed by the politics. I've been doing this for decades, and I've been 8 years advising the German government in an official government advisory group appointed by the government, and they are not really listening to us very much. So it is often also a bit depressing, but I also see a lot of positive signs. For example, when I was young, even older than you, but at that time, we were told that only at best 3% of electricity could be generated by renewables, so wind and solar. Now in Germany, we're at 50%. So in the part of the solutions, what we can actually do with technology to help solve the climate crisis, things have been a lot better than expected. The growth of these technologies is phenomenal, the improvement in the technologies. So in terms of our ability to solve this, things are much better than we even thought 10 years ago. So there is good reasons for hope.
Yes, please.
Thank you for your lecture, and thanks for coming to bring awareness in the fourth largest country in the world. It means something, Professor. So my question is, I'm a teacher here, I'm a science teacher by working holiday, but I also do community development all over Indonesia during holiday. So we try to bring the sustainability issues in the rural areas, in the remote areas. And one of the biggest issues that we have is that although we bring science to solve their small problems and try to balance between health, economy, and climate change, and etc. in their daily life, we are faced with sometimes with politicians who try to do what are you doing, for example, because we try to explain that what we do, this local solution for the local problem that the community has. For example, I will give you a concrete example, the things that I do in Banda Neira, where the fishermen rely on the middlemen to bring the fish to Ambon and then later on to be exported or to be sent to Jakarta. When the middleman ship is full, then the fishermen cannot transport the fish anymore, and they dump tons of fish, fresh fish, back into the harbor, just like that. And at the same time, people in the East suffer a lot from stunting. 50% of children don't eat enough protein. So we try to bring simple solution by canning this fish so that they can preserve it, and then they eat it themselves because they don't have refrigerators or ice to keep the fish. And this simple solution actually works, but we cannot convince people whether what we do is, we try to reduce carbon here. We try to be carbon neutral here, but is there a calculator? I know there is a calculator online where you can really measure this activity, release how much carbon approximately and how much you can save, but in a small scale, sometimes we doubt ourselves whether what we do trying to balance all these activities in terms of reducing the carbon into the air without sacrificing the human life and trying to improve their livelihood really actually works, whether we are doing the right thing. Is there any suggestion from your side how to somehow calculate that we are going towards carbon neutral, that we are doing the right thing?
Okay. Well, I can only applaud your efforts, but I think I can't help you with this problem, and I don't know how important it is if you are really helping the people on the ground, etc., to have an exact carbon calculation or so. I think it's probably a secondary issue for the people concerned, right? Yeah, I mean that there are scientists that do all this kind of analysis. And I'm doing just more basic climate research, and it is indeed, it's not easy to, if you have several components and transport emissions and all these things involved, it's not easy to do this calculation. So I don't think I can give you any helpful advice here.
There's another question from Max, I think. Max or Eldin, or where's the microphone?
Sorry, I Is it okay if I ask the question?
Who is it? Just go ahead.
All right. I think I would just like to introduce myself before I ask the question. I'm from Mentari Intercultural School, Bintaro, and I'm here with my lovely science teachers here. I would just like to thank you for the wonderful presentation, and I would just like to say that there's a lot of links with our studies in environmental systems and societies, which was pretty interesting. So my question was actually relatively tied to the previous questions, which is, what, you as a scientist, what do you think is your personal viewpoint on the current state of urgency with, I think, specifically with governmental bodies, I think specifically maybe with like United Nations Environmental Program? Do you think that they are doing as much action as they have promised us, or do you think that it's been significant to the development of overcoming climate change?
Well, obviously, the political action is not enough, because even though the emissions should be dropping dramatically fast now, they are still rising. That is bad. The good thing is that the International Energy Agency predicts that probably this year this is the maximum of the emissions, so that from now on in the next years they will start going down. That, I think, would be psychologically a huge turning point if we see that we actually manage to bend the emissions curve down. I hope this will actually happen. We will see in the next couple of years. But then, of course, we need to fight to make the emissions drop faster. I think, it's definitely not enough. And of course, the United Nations don't have the power to do that, because the power rests with the national governments, and unfortunately also with big international corporations that have an undue influence on politics.
Now, I've got one question coming in from the live stream. Someone is asking, the argument is that it's unfair that developed nations in Europe got their chance to industrialize while we haven't. What would be the best way to respond to this? And he's going on with, it's encouraging that globally there is more awareness now, but in emerging countries like Indonesia, there is a stronger focus on economic development than climate.
Yes, it is absolutely correct that the wealthy industrial nations are so far the main culprits, because they have, of course, developed based on fossil fuels and are responsible for the bulk of the carbon dioxide emissions so far. And there is a lot of responsibility resting with countries like Germany or others like the United States in that regard, to help other nations that have contributed not so much in terms of emissions to make this a transition. It's the energy transition. It's not a question of either climate protection or economic development, because we can actually have both. It's just the question, what kind of development? And I've already mentioned that solar energy is already the cheapest energy form in most places, and there is no contradiction between economic development and climate protection. The main contradiction is now that those actors, the big corporations that live on selling fossil fuels, are really resisting the change. I think that is the biggest problem here that we're facing, and we all need to work together. Some developing nations, of course, have a share in the problem, as I mentioned, about a quarter coming from deforestation, and that, of course, is their government's responsibility to stop that. Much of it, like in Brazil, is illegal deforestation, and there the governments have to make more efforts so that this is stopped.
Are there any more
Hello?
questions?
Yeah.
Here.
I My name is Maximilian. I'm in grade 12, and first of all, on behalf of the school, thank you for coming. And my question is, you said in your presentation that the Atlantic Ocean is actually getting colder. Wouldn't that affect the ecosystem? And if yes, how would it affect it?
Very good question. We tried to study this. That means with international partners from Scandinavia, from Iceland, etc. We made a big scientific research proposal to the European Union, but it didn't get funded, and so we haven't done the research how it affects the ecosystems. So I can't answer your question, but it is clear that it will have a big effect on the ecosystem, except without actually doing the research, we can't really tell how exactly this looks like.
Frau Kuttig hat das Mikrofon, habe ich gesehen. Oder ist ja, okay. Ja.
What's happen if there is just an ocean, no island? What's happened?
You mean a planet entirely covered by ocean?
Yeah.
Well, this is a good question that scientists have also asked themselves, and they have actually run the simulations. So there is a branch of climate model simulations which we call Aquaplanet. So it's an Earth entirely with ocean. And then, of course, one thing that happens, probably the biggest, is you get an entirely different ocean circulation. The ocean currents are not moving in north-south direction anymore. They all kind of align in east-west bands. That has to do with this Coriolis force that I mentioned, and it is what you can see if you look at a photo of the planet Jupiter, for example. We see it has all these cloud bands that are aligned along the latitude circles, because on a rotating ball, that is a preferred direction of motion, because it's quite hard to move in north-south direction, and so because of that changing Coriolis force with latitude. And so, yeah, that's the biggest change that would happen in that respect.
Whose turn is it now? Ja, Frau Kuttig.
Yes, I've got one question and one request. My question would be, you haven't mentioned it, but do you have any hopes for resolutions or maybe even decisions being taken at COP28 at the end of this month? And my request would be maybe towards the end of the session, if you could give especially the students who've been studying climate change some advice on how to handle climate anxiety, because I know that students at the school are afraid of what's happening and what might be a possible future, especially for them. And maybe you have some ideas or also some web pages that put a more positive, or shed a more positive light on the future.
Yes, good questions. To those who don't know, COP28 is the next annual global climate summit coming up. It's the 28th, so these COPs have been taken place nearly annually since the Rio Earth Summit in 1992, and so we're now at the COP28. Yeah, you know, I'm just doing basic science, and these COPs are, of course, done by the policy community. Maybe Maike can comment what the German government expects for or hopes for COP28. I'm just kind of learning this from the media. I actually listened to a podcast yesterday about that, but I don't know much about it. Maybe you can comment after me. The anxiety issue, I think important is to talk about your concerns, to find like-minded people, maybe a group, whatever, Fridays for Future or so, make a local group, because every problem is easier if you share it with other people and are able to talk about it, etc. And as I mentioned, don't ignore all the hopeful developments. The news, of course, and that's unfortunate when you follow news, that they tend to focus on the negative news, and it's easy to get depressed. Don't forget to see the positive side, the hopeful things like the rise of the Fridays for Future movement, the changes, positive changes in the energy sector that are happening now, and so on.
Maybe, thank you. Maybe one last question for our community also. You said the main responsibility to solve problems are with the governments, but isn't this quite convenient for the individual just to wait what the government allows or forbids, or isn't it worth the effort for each single individual to do the best what they can, even if it's just to not use single-use plastic bottles to save the energy and the CO2 related to such things?
Yeah, I think that's a very good question, and it is of course not either or, you know, it's not just only leave it to the governments and do nothing yourselves. Everyone can do something themselves, like you know, reducing airplane use. This is really kind of a big chunk of emissions. If you fly to Germany, for example, or I fly here, and you know, for my private holidays I go by train in Germany, and as I said, I have solar panels on the roof, and I don't own a car. All my life I've done everything with a bicycle. I think that's pretty tough in Jakarta. From my first impression, I've only been here for less than 2 days, so I shouldn't comment on that. But the question, you know, what can you do as an individual? You can do a lot, but I think maybe more important than this famous carbon footprint of how much emissions you're actually causing is your handprint, and that is what you're actively doing, say going to a climate protest, informing others about the problem, when you're old enough, voting, you know, who do you vote for, this kind of things, how you influence things around you beyond your personal carbon footprint is often more important than handprint. And I think everyone can do a lot. You don't have to be perfect, like, you know, you basically individually you cannot get to zero emissions, even if you do all the best things that are recommended. If you go to an online emissions calculator, your carbon footprint, you know, as a German, I have done that, of course, and in the carbon calculator from the German Environment Agency, I have chosen all the best options what I can do as an individual. Only use local food, don't travel on airplanes, don't drive a car, etc. You still use your I would reduce my emissions compared to what they are now by less than half. It's still, the majority of emissions is still there, and so as an individual you cannot get to zero emissions. That has to be a structural change to the way how we produce our energy, how we produce our food, and all these things.
Thank you. Last question.
Moment, yes, okay. First, I want to say, students, you were great. You were great listeners. Yes, yes, yes. Jaden is shaking his head. You did great. Thank you very much for the presentation. I've got a very last question, a quick one. But before I ask that, I want to ask Mr. Hoffman to make our lunch break longer.
Yeah, I think this is no big deal. We just make it 15 minutes longer. Yeah, so what? Yeah. Yeah. So, the last question.
Okay, my last question. You mentioned the Maldives, but you did not say anything about the immediate effects on Indonesia. What do you think about Indonesia's future having 17,000 islands and about Jakarta's future? Jakarta, I mean, for good reasons, the capital of Indonesia has moved to another part of Indonesia. So what do you think about our future here in this country?
Well, of course, I know a lot less about this than your local scientists that you have here in Indonesia as well. But it's obvious that all islands, like Indonesia, will be strongly affected by rising sea levels. And Indonesia, like many other places in the world, is probably at risk from increasing drought problems, simply because in a warmer climate you get more evaporation. Soils, trees lose their moisture faster, even if the rain stays the same. But rainfall changes are very hard to predict. But if it's true that you get stronger El Nino events, that obviously is also a drought risk for Indonesia.
Okay,
Yeah,
that was it.
thank you.
20 minutes longer break, guys.
Yeah, so there's one hand, I see still one
sorry.
hand.
So, what is a good substitute for fossil fuel?
The substitute, you said, for fossil fuels? Well, in many cases, when you're talking about electricity, it is the wind and solar power. And for other areas where it's not used for electricity, like, for example, heating with gas or steel production, you can actually use technologies to also use electricity for that. For heating, you can use heat pumps like I have in my house. And even for steel production, I have just seen that a British company has moved from the gas furnaces to produce the steel to electric furnaces. These things are possible. For cars, you can switch to electric cars and then generate the electricity with wind and solar. So a big electrification of many sectors is key, and then renewable energies.
Okay, thank you very much. And please give Herr Professor Rahmsdorf a big applause. Yeah.
Thank you, thank you.
So,
Oh, thanks. And thanks for the really good questions, and thanks for listening. I'm really impressed. Thanks.
ja, wir haben noch ein kleines Abschiedsgeschenk. Nicht besonders nachhaltig verpackt, aber es kommt sehr von Herzen und eine Tasse und eine Tasche. 2 Euro für die Schule. Ja? Ja, okay.
Presents, so like politicians.
Ja. Und man hört ja